Let's look at what happens if these equal mass cars, if I've got the two equal mass cars, can move, but let's see what happens if the collision is inelastic, or if they stick together. So now instead of little magnets here, I've got little pieces of Velcro, and when the cars collide, they'll stick together. So let's watch what happens again. I'll have one car starting at rest, and the second car will come in, and we will see what happens when they stick together. Again, observe velocities, observe momentum transfer. Alright, let's show that one more time. Maybe I'll make it go a little bit faster. Notice what happens as they come in. Comes in. We notice in this problem that the cars that stick together leave with the same velocity. So let's do our little sketch. I've got my two boxes. This is before the collision. So before the collision, I've got a 2 kilogram box and a 2 kilogram cart that are both moving. Again, this one started with a velocity of 0, and this one started with a velocity of 5 meters per second, and it was moving in this direction. So before the collision, we end up with a cart that looks like this. After the collision, it's a little bit different because we have two carts that are stuck together. So we'll just draw them like this, like the little Velcros stick together, 2 kilograms, 2 kilograms. And we noticed that the velocity changed. Obviously this one had a 0 velocity sped up, and it looked like this one slowed down a little bit, but we don't know what that velocity was. We can use conservation of momentum to help us to calculate that. So our general procedure, write down the total momentum before the collision. Momentum is mass times velocity plus mass times velocity for the second cart. So we get 2 kilograms times 5 meters per second plus 2 kilograms times 0 meters per second. So we end up with 10 kilogram meters per second plus 0, or we get 10 kilogram meters per second. That's the total momentum for both cars before the collision. Let's do the same thing over here after the collision. After the collision, my momentum is, well, the two cars are combined together now, so it's 2 kilograms plus 2 kilograms. That's my total mass times my velocity, but I don't know my velocity. So the momentum is going to be 4 kilograms times the velocity. And that's the best I can do. I'm done. I don't know the velocity, so I can't do anything else. But again, because of conservation of momentum, the momentum before the collision and the momentum after the collision are equal. Momentum is conserved. So I can do that inequality, and I can say 10 kilogram meters per second is equal to 4 kilograms times my unknown velocity. And that's easy to solve for. Divide by 4 kilograms, divide by 4 kilograms, and I end up with velocity equal to 2.5 kilogram meter, velocity, no kilograms, meters per second. My kilograms canceled out here. So 2.5 meters per second. And again, we can go back and interpret this. We can say, well, gee, what happened? This car was moving 5 meters per second, and after the collision, it's moving 2.5 meters per second, so it slowed down, and that makes sense. This car was moving 0, and afterwards it's moving 2.5. It sped up. That also makes sense. Something hit it to cause it to speed up. So the question becomes, based on conservation of momentum, these colliding cars that stick together end up having a velocity that is halfway between them. Is that always going to be the case, that the velocity is halfway between them, or is that a special case because our masses happen to be the same? So that may be something we'll want to study at some point, is what happens if these masses change, or what happens if this guy doesn't have a 0 velocity? Does that change anything? So we might look at that in the future.